Hi everyone, in today's video I'll show you how to run factor-based regression analysis on survey data. But before we jump into the technical steps, let's quickly understand why we even do this. As data analysts, we often work with survey data where people answer dozens of questions, some with ratings, some yes or no, and some multiple choice. The problem is many of these questions overlap in meaning. For example, people might answer several different questions that all reflect the same idea, is it like trust, satisfaction, or convenience? If we just plug all of those questions into a regression, it causes confusion and can mess up the results because the variables are too similar to each other. So what we do is we group related questions into bigger themes called factors using a technique called principal component analysis or PCA. Then we run the regression on those factors instead of individual questions. This helps us get a much clearer picture of what really matters, like which area, such as trust or service quality, is having the biggest impact on customer satisfaction. And ultimately, we use these insights to make data-driven recommendations for our clients, helping them focus on the specific areas that have the biggest impact on overall satisfaction. So let's get started and walk through the process step by step, from raw survey data all the way to clear actionable insights. Let's dive right in. Let's say you've collected data from a survey. Some questions were rated from 0 to 10, others were yes, no, and some were multiple choice. Now, the challenge is how do we standardize all of this so we can analyze it together? That's where scoring comes in. We begin by converting responses to numeric scores. If a question was rated from 0 to 10, we multiply it by 10 to convert it to a 100-point scale. If the response is yes or no, we assign yes equals 100 and no equals 0. And for missing answers, we handle them using a denominator where answered equals 1 and unanswered equals 0. We do this for all questions to make sure scores are consistent and comparable across question types. Now that we've created numerators and denominators, we divide the numerator by the denominator to calculate the final score per question. This helps us normalize all question data to a common scale and filter out missing responses. You'll compute these scores using the compute command in SPSS. After computing all question scores, we label them. For example, trust, respect, knowledge, and so on. These become our EQ variables. Now, why do we perform PCA here? Because many of these questions are highly correlated. Running regression with collinear variables violates statistical assumptions. PCA helps reduce dimensionality and group similar variables into factors. This allows us to create composite variables, factors that are independent of each other. Now we open SPSS and load our processed dataset. Go to Analyze, Dimension Reduction, Factor. Here's what you do. Select all EQ variables except the dependent variable. Under Extraction, choose Fixed Number of Factors and input the number of independent variables, e.g. 17. Set Iterations, try 100. Under Rotation, choose Equimax for balance between Varimax and Quantimax. Under Options, check Sorted by Size and set the minimum coefficient to 0.6 to clean up the output. Save the factors as regression variables. Now click OK. SPSS will now group your variables into meaningful factors, which you'll see in the rotated component matrix. Once you've created the factors FAC1, 1, FAC2, 1, etc., go to Analyze, Regression, Linear Set. Your dependent variable, e.g. EQ1, customer satisfaction. Set your independent variables as all the factors generated from PCA. Click OK. Now SPSS runs your regression analysis. You'll see a few key tables in the output. Model summary, look at adjusted R squared. This tells you how much variance in your dependent variable, e.g. customer satisfaction, is explained by your factors. A value like 0.81 means 81% of variation is explained. Very strong coefficients. Table. This is where the real deal is. Each factor has a beta coefficient showing its impact on the dependent variable, a sigma value, p-value. If it's less than 0.1, the factor is statistically significant. Now here's the important part. If any factor has a high p-value, e.g., greater than 0.1, it means it's not significantly contributing to the model. You may consider dropping it and rerunning the regression for a cleaner, more accurate model. And that's how you do factor-based regression using PCA in SPSS, starting from raw survey data to normalized scores to creating independent factors, and finally running a regression to find out which factors impact your target outcome the most. If you found this helpful, hit that like button and subscribe for more data analysis tutorials. See you in the next video.